Hello there. In this lesson, we're going to learn about synthesis and decomposition reactions. If you've ever played with steel wool and lit it on fire with, a match or a battery, that's a synthesis reaction going on there. You're reacting some of the iron in the steel wool with oxygen in the air with a little heat. You end up making some iron oxide. And so it's this rapid reaction, looks really pretty. And so that's what we're going to talk about today, synthesis and decomposition reactions, where you're either putting things together to make a compound or taking compound apart. So we'll start with synthesis reactions. Synthesis reactions occur whenever you have two reactants combining to make a product of some sort. Generally, it's, you got A plus B, you're going to make two things together. Just like in the previous example with burning the steel wool, when your car is rusting, it's the same reaction. You've got iron plus oxygen, and we'll make Fe2O3, which is iron 3 oxide, as a product, right? And so that product, obviously a new substance, is the result of combining two reactants. So it can be two reactants that are elements, and sometimes it's two reactants that are compounds already. So since our atmosphere has lots of oxygen in it, and oxygen's pretty reactive, oxides are a pretty common substance that forms naturally or can be formed on purpose for various reasons. And so what happens is that metals can react with oxygen to give you metal oxides, like this magnesium that's reacting here. When it burns, it's very bright. Or even nonmetals. So lots of nonmetals will react with oxygen and give you nonmetal oxides. So if you burn, say, some charcoal carbon in oxygen, you'll get carbon dioxide as a product. So oxides are a great example of synthesis reactions. So when oxides are added with water, you get a good example of a synthesis reaction that occurs between two compounds rather than two elements. And so what you end up with, if you take some magnesium oxide, which is that white powdery stuff that we got left over from burning the magnesium, and you drop it into some water, you'll see that the water with some indicator in here turns a kind of pink color. So this is a phenolphthalein, which is pink in a base. And so whenever you add one of these metal oxides to water, you'll often get pink color with your indicator, because a base is what will form. And so that's a synthesis reaction, because we're taking two smaller compounds and making a third larger one. So it doesn't matter what the metal is, you'll get the same product. It'll still be a hydroxide. So lithium oxide and water would give you lithium hydroxide. You'd have to balance that out, but that would be the product. Aluminum oxide and water would give you aluminum hydroxide. Just make sure it balances out correctly. We can balance these together if you want to here. We got two lithiums, and let's see here, we got two oxygens, two hydrogens. I think that one's good. Here we got two aluminums, so we're going to need two there. And let's see how we got 3 times 2 is 6 hydrogens, so we're going to need a 3 there, and that takes care of the rest of it. Great. All right, so there you go. Some synthesis reactions that use compounds rather than elements. Now, nonmetal oxides can also react with water to form products as well. This time you don't get a base, you get an acid. So there are a bunch of different acids. Probably the most commonly known ones are the ones that form acid rain. When we burn fossil fuels in our vehicles or factories, there's lots of oxides that form from burning, things like sulfur trioxide and nitrogen dioxide. And what can happen is that these can go up and go through a couple chemical steps in order to end up producing acids like sulfuric acid and nitric acid. And both of these are pretty harmful to the environment. Yeah, so there you go. Another synthesis reaction where it's compounds that are reacting together to give you a product. So non-metal oxides and water will give you an acid. When you take two types of oxides, a metal oxide, non-metal oxide, you can get a compound as well. So if we take our magnesium oxide and carbon dioxide, you can think of this extra oxygen going with the two that are already with the carbon dioxide, and you end up with a carbonate ion and a magnesium ion, magnesium carbonate. Sulfur trioxide can do the same sort of thing. If you combine it with calcium oxide, you just end up with calcium sulfate, which is a nice addition to do there. You don't even have to do any balancing. Decomposition reactions are more or less the reverse of a synthesis reaction, and they can be carried out usually by adding energy or using a catalyst to get a compound to break down into its component parts. So you'll have one larger reactant that you're starting with, and you'll break it down into smaller parts. And again, just like the synthesis reactions, those smaller parts can be elements, or they can just be smaller compounds. This one's a classic one, which is the electrolysis of water. This is how they'll make oxygen on, say, a submarine that's down under the water for a long time. What you can do is you can take some of that seawater and you run some electricity through it, and you see these bubbles going up here. On one side you'll have hydrogen, and the other side you'll have oxygen, and that will break the water apart into its component parts. So you start with water, you add some electricity, and you end up with hydrogen and oxygen. And then of course you need to balance it. And over here we can say electricity to make it happen. So energy is one way to get a decomposition to happen. Usually you need it to break apart that compound that you're starting with. So sometimes it's electricity, like you saw with the electrolysis there. Other times it's heat. If you heat up reactants enough, they can break down into their component parts. And another way to do that is to add a catalyst. So catalysts are interesting because they will lower the amount of energy needed for a reaction to occur. And so you can just add the catalyst and it will help a reaction go faster without being actually used up. So in this reaction, you can see here, I'm pouring in a catalyst. It helps the breakdown of hydrogen peroxide in here, which is everyone's favorite elephant toothpaste. So you got H2O2 in there. And H2O2 is fairly stable. It'll sit there by itself, not doing much of anything until you throw that catalyst in there, and that rapidly speeds up. Usually the catalyst is potassium iodide, and it'll rapidly speed up the reaction, and you get these bubbles made that are lots of fun. So your acids and bases that you formed by synthesis can also be reversed if the conditions are correct. One good example is carbonic acid in soda. So if you have any sort of soda water or pop, there'll be carbonic acid like dissolved in there, it'll be aqueous. And when you release the pressure, out come these little bubbles. The bubbles are carbon dioxide, and what's left behind is just water. So that carbonated water is held in there under pressure, and when you release the pressure, a lot of it converts into carbon dioxide. So you get water and the carbon dioxide, which are the gas, the bubbles. Some bases can do the same thing. If you have them, say, in their solid form, you can heat them up and you'll get them decomposing again back to their oxides and water that will be driven off. Good old water, the liquid. Calcium oxide would be a solid because it's an ionic compound. A few others to note that are fairly common. Carbonates, like the ones found in limestone, are often heated up in order to make the raw materials for things like concrete. And so if you take some calcium carbonate, which is in limestone, and you heat it up, you'll end up with that calcium oxide again, and you'll drive off some carbon dioxide. This is why the concrete industry is a big producer of greenhouse gases, because they make so much of this carbon dioxide by heating up limestone. What else do we have here? We got nitrates. Nitrates are strange in that you get 3 products instead of just 1, or 2, I should say. So you get the calcium oxide again, of course. You'll get some nitrogen dioxide, and you'll have some oxygen as well. So these are a little unusual pattern for many nitrates. They break down in this way. You get two gases that are formed and one solid. Finally, we got our chlorates. This one is often used in class when we do what we call the screaming gummy bear. And if you heat up some sodium chloride enough, it'll break down into some sodium chloride, and you'll end up with some oxygen gas there as well. And so when you heat it up and you get lots of this oxygen gas available, well then whatever you drop in there will burn like crazy because there's all this super hot oxygen that's waiting to react with something.